So given the importance of the null space, let's take some time to work some examples where we compute bases for the null space and use this to interpret our solution spaces. Our first example is a toy example. It's not interesting from a technical standpoint, but it is really enlightening from a geometric perspective. So we're going to consider a matrix transformation from R2 to R1. And this matrix transformation is going to take in a vector expressed in the coordinates x and y, and it's going to output the matrix product 1, 0 multiplied by xy. This, of course, is simply the element x. This transformation is usually called the projection onto the x-axis. This is because every vector in R2 simply gets mapped to its x-coordinate. Of course, the null space for this transformation is really easy to identify. The only things that are going to get mapped to 0 are the vectors which have x-coordinate 0. And of course, this is exactly what you think it is. It's just the y-axis. So if I were to draw this transformation, I could think about this as squishing the y-axis down to a single point. My cartoon picture would be an R2 above R. So I like to draw R2 simply as the XY plane. And I like to think about R1 as just a line, a horizontal line. In this case, I'm going to label it the x-axis. So my coordinates sort of agree here. And I like to think about my mapping, which I'm going to call T, as taking this line, which is my y-axis, and mapping all of those points down to the single point at 0, which is the origin of the real numbers. So I've highlighted these two pieces to sort of indicate that they're being identified. And I have this arrow, which sort of serves as the mapping indicator. Now, if we're thinking about a solution space to an equation that is not the homogeneous equation, then we're thinking about choosing a non-zero real number. Let's call it A. In my picture, A happens to be a positive number, but it could also be a negative number. There's nothing particularly special about the fact that it was positive. It's just non-zero. This notion of translation carries through in the following way. We start out with the equation t applied to xy is equal to a. The solutions to this, it's pretty easy to see, are all of the vectors whose x-coordinate is simply a. Well, we can think about all of those points as a vertical line, right? This is just the equation x equals a in R2. Now, I can think about the same sort of mapping from this vertical line, just squish it down to a point. But of course, I can always think about any vertical line as being a translation of the vertical line x equals 0. All I have to do is simply take this line and translate it by a units. If a is positive, I move to the right. If a is negative, of course, I would translate to the left. So in this way, we can see that the shape of the null space, in this case a one-dimensional subspace of R2, dictates exactly the shape of all the other solution spaces. So it's important to note that these are absolutely not subspaces of R2, in particular because they do not pass through the origin. No subset that does not pass through the origin can be a subspace. That's never ever true. However, this notion of dimension or maybe shape is applicable because we can think about these solution spaces simply as translations of these lines by a vector. In particular, we can see this explicitly from the algebra by breaking apart the line x equals a as not the vector ay, but as the vector a0 plus the line 0y, where y is the variable and a is simply a fixed number. So this intuition is very useful in spaces where it's harder to sketch a picture. For example, let's try to understand a slightly more technical example in R3. So we have a matrix A with 3 columns, V1, V2, and V3. If we label the coordinates for R3 as x, y, and z, then we can see that y and z will be free variables. The solution space to the homogeneous equation is described by the single equation x plus 2y plus 3z is equal to 0, which of course we can rewrite as x is equal to negative 2y minus 3z. And we can express this as a set of vectors parametrized by the values y and z as xyz is equal to, simply replace x by negative 2y minus 3z, then break it apart into the sum of 2 vectors, the first one scaled by y, the second one scaled by z. So of course, this allows us to express the null space as a 2-dimensional subspace of R3 spanned by these 2 vectors, minus 2, 1, 0, which we'll call U1, and minus 3, 0, 1, which we'll call U2. Next, you could check with Sage that the matrix with columns U1 and U2 will have 2 pivot positions. This tells us that our 2 vectors, U1 and U2, are linearly independent. So in fact, this is a subspace of R3 of dimension 2. Therefore, we can think about the null space of A as the plane through the origin described by either the equation x plus 2y plus 3z is 0, or as the span of these 2 vectors, u1 and u2. Now, let's assume that we'd like to find the solutions to the equation ax is equal to 6, 12, 18. Now, we can of course solve this equation exactly the same way that we would solve the homogeneous equation. We can of course interpret this as the equation x plus 2y plus 3z is equal to 6. Now, if we're thinking about the solutions to the equation ax equals b as the set of all vectors whose x-coordinate plus twice the y-coordinate plus 3 times the z-coordinate is equal to 6, we can find a particular solution to this equation by simply choosing x to be 6, y to be 0, and z to be 0. To find all the solutions, we simply have to take this vector and use it to translate our null space. So we can see that the set of all solutions to the equation ax equals 6, 12, 18 is given by the set of vectors 6, 0, 0 plus y times negative 2, 1, 0 plus z times negative 3, 0, 1, which is of course the same thing as the set of all points in R3 or all vectors in R3 whose coordinates satisfy x plus 2y plus 3z is equal to 6. So we can think about this as having started with a plane through the origin given by x plus 2y plus 3z, and then having translated this plane so that it now passes not through the point 0, 0, 0, but through the point 6, 0, 0. So this is a plane that is parallel to the null space. So as a final example, let's consider the following 3 by 5 matrix. This matrix defines a transformation T which takes in a vector of dimension 5 and outputs a vector of dimension 3. So that tells us that our null space should be a subspace of R5. If we ask Sage to place this matrix into reduced row echelon form, if we label the coordinates for R5 as x1 through x5, then this will give us two equations. The first row corresponds to the equation x1 minus 2x3 minus 3x4 will be equal to 0. The second will give us x2 plus x3 plus x4 minus 2x5 is equal to 0. So to understand the null space, we use the columns without a pivot. Those are the ones corresponding to the variables x3, x4, and x5 as our free variables. And we can express the vectors that A, or the transformation T, maps to 0 as those whose first coordinate is 2x3 plus 3x4. Second coordinate is negative x3 minus x4 plus 2x5. And then the coordinates x3 through x5 are free. So of course, we can separate this into three vectors. The first one is x3 times 2 minus 1, 1, 0, 0. Second is x4 times 3, negative 1, 0, 1, 0. And the third is x5 times 0, 2, 0, 0, 1. So if we name these three vectors, let's say u1, u2, and u3, then we can see that our null space is three-dimensional. It's going to be spanned by the three linearly independent vectors u1, u2, and u3. Alternatively, you can think about the null space of A as the set of vectors or as the set of points in R5, since we have a tendency to identify those, whose coordinates satisfy the two equations, x1 minus 2x3 minus 3x4 is equal to 0, and x2 plus x3 plus x4 minus 2x5 is equal to 0 as well. And note here that these are simultaneously true. So the vectors have to satisfy the first equation and the second equation. So in the next video, we're going to talk about our last important subspace that is attached to a matrix.